Um, all right. Does anybody have any questions from last week? This is the list that we generated last week in terms of issues and concepts that people didn't understand out of the paper. We can always add more to this um, if necessary. And if not, then we're just going to continue where we left off.
Cool.
All right, cool. All right, so yeah, so let's start here. You guys see, yeah. All right. So to talk about, so we're going to talk about confidence intervals, and then we're going to talk about relative risk, and we'll see how far that takes us, because they're both related, and they're really important concepts, especially in this particular paper. But they're really important concepts in general because these are statistics that are really commonly used, and confidence intervals are huge. Like you use them for almost everything. So if you don't understand the concept of a confidence interval, then almost every paper you read, you're probably not going to get. And they're really, really important. So to get to the confidence interval, we have to talk about standard deviation and then standard error and what the difference is between those two. And then we also have to talk about things like the concept of what a population estimate is versus a sample estimate, and how they all relate to one another and how we get there, sort of, so to speak. Because statistics they're basically math. So somebody did all the hard work in the late 1800s and early 1900s, and then now we just use their work. And so you can, with certain programs, just plug in numbers onto a spreadsheet and get something out at the other end. And if you don't know how to interpret that, then you are eventually going to write a bad paper. So let's talk about standard deviation. So when we talk about taking a mean of something, so everybody knows, I'm thinking that a mean is when you just add up all the values of whatever it is that you've measured from wherever you got it from, and then you divide it from the number of things that you measured. So if you're measuring the height of basketball players on a certain team, then the mean height is the sum of all of the heights of the basketball players divided by the number of basketball players, right? So that's a good sort of middle. That's your middle number, and then a standard deviation is, well, what's a representative range of that number? So is your basketball team composed of really just all tall people and that's it, right? So you might have like a mean of like 6'4", and your standard deviation is only like 2 inches, right? So from what we talked about last week in terms of a normal distribution, 66% of all your basketball players are going to be within 2 inches of 6'4", and then 95 or 96% of all your basketball players are going to lie between 6'0" and 6'8", right? So that's how that normal distribution and standard deviation comes together. So the standard deviation gives you the rough variability, not the rough, it's the calculated variability of the range of all the values that you collected. So you calculate a standard deviation by taking the distance from the mean of every single data point that you gathered. So in the case of these basketball players, you take every basketball player and you find out how far away they are from 6'4". And you add up all those distances, which is composed of both both negative and positive numbers, and you square that, and then so that you can avoid getting the negative numbers as negatives, and then you divide it by n-1, and we don't have to talk about why it's n-1, okay? And then you take the square root of all of that to get rid of the square that you did at the beginning, okay? So what that does is basically, if your mean is here, and let's pretend this is 6'4", and you measured like, 8 basketball players, they would, some of them would have heights that like maybe lie right on the mean. Some of them might be taller, some of them might be shorter. Right, let's make this one really tall. Okay, so when you measure the standard deviation, you're taking the distance from here to here, here to here. This person's on the mean, this person's on the mean, here to here, here to here, and here to here. Okay, and you're basically adding those up, and roughly you're basically adding them up and dividing them by the number of players. So it's the mean distance that you're actually calculating via doing like a bunch of squares and square roots, because you have to, you can't, if you start adding the negatives, then you're going to end up with 0, and that's not really the case. All right, so how does this relate to standard error and a confidence interval? So this is why we need to talk about population versus sample. So samples are estimates of the population. So there's like, when you use the term population estimate, it's a very specific definition, right? So what we're trying to do is we're trying to take a small sample of a larger population and figure out something about that larger population, right? But because for logistic reasons, we can't measure the entire population, we have to infer from the sample that we collected something about that bigger population. So when we measure the heights of everybody on one basketball team, we are trying to figure out, really at the end of the day, maybe what the height is of all basketball players on all basketball teams in the entire world, right? And so your sample mean is an estimate of that population mean, and the population would be all basketball players in the world, right? So what happens when we do this over and over and over again? So let's say we sample, like 10 teams. The more samples that we take, the closer to the truth that we get, because we come closer and closer to actually measuring every single basketball player in the world, right? And so there's this thing called the central limit theorem, which I won't get into, but basically what it says is that as you repeat estimates of the population from samples, you're going to eventually get a normal distribution of estimates. So if we measure, let's pretend we measure 6 basketball teams, all right? And the mean height, 6'4", see, I don't know why I'm doing decimals there. Let's say it's pretty narrow, right? So some of them are pretty tall, and these are just means. So mean, 6'1", 5'11", and 6'5".
These would be the means of various teams, Brian?
Yeah, this is the mean height of various teams.
Okay.
The more that we do this, if we kept going and going and going, eventually we would measure all of the basketball players in the world, right? When you plot this out, and so right here is going to be height, mean height, all right, versus, well, this is just versus the ordered frequency. Is that right? Let me think here. No, it's the other way around. So this is frequency, and this is mean height. So if you were somehow omniscient, you would know the mean height of all basketball players in the world, right? And that's going to be right here. Okay. The more samples that you take here, the more this curve eventually is going to look like this. Sorry, let's do a different color. All right. Where you have you're going to have a large cluster of samples that are actually pretty good estimates of the true mean height of all basketball players in the world. And then you're going to have some that are maybe not so good estimates of the true mean height of all the basketball players in the world, right? So when we talk about the population estimate from a sample, what we're talking about is where on this, what we want to know is where on this, sorry, I'm doing the waving my thing over the screen again where you guys can't see anything. Yeah. What we want to know is like, where on this curve is our estimate? Are we here or are we out here? All right. And so this is where standard error comes into play. So standard error mathematically is the standard deviation divided by the square root of n of the number that's in your sample. Okay. And the derivation of that equation comes from the central limit theorem, which I don't think we have to talk in great detail about for now. And that might be something that we explore near the future when things get a little more deep. But for now, it's just easier to say the central limit theorem says this equation works, okay? And so the standard error is basically simply defined as the standard deviation of the sampling distribution of the population, okay? So remember, I'm gonna draw our little graph again. So this is frequency, and this is mean height. All right, and we had something that looked like that, and that's where this is the truth, the objective truth, okay? So the standard error is basically the standard deviation of this, sorry, of this graph, okay? So the same rules apply. Remember we talked about 66% within one standard deviation and 96% roughly within two standard deviations, right? So when you calculate your standard error, what you're doing is you're trying to figure out what is the rough, what is the estimate of this range if I do this over and over and over and over and over again with the same number of players. So if I sample one basketball team that is 8 players, not sorry, see, I'm making this, you guys are letting me embarrass me again. So if you sample 8 basketball players at a time, right, then and you do that over and over and over again, you're going to get a curve that looks like this. If you sampled 20 basketball players at a time, you might get a curve that looks a little bit more like this. Where, sorry, you'll get the same curve, it'll just be different. You'll still get the same curve, but the intervals will be much narrower. Right? So you're going to get 66% within a much narrower margin. You're going to get 96% again within a much narrower margin because you're getting closer to measuring everybody. Okay. Does that make sense? Yeah. Okay. So that's great. So you have the standard error, which estimates the standard deviation of this graph, okay, of this curve. But that's not necessarily informative. It doesn't help you really know what it is that you're dealing with because you have to do all this math in your head and it's hard to conceptualize that. So that's why we have a confidence interval. That's why the confidence interval ultimately, I think, was created, or yeah, created, all right? Because it gives you a much better idea of how to interpret that standard error. And it gives you a much better idea of how precise your estimate of the population actually is. So a confidence interval, the equation for a confidence interval changes depending on what it is that you're measuring. So if you're just measuring averages, the formula for a confidence interval is roughly this. And this is a slightly simplified formula, but it works most of the time. The 1.96 is what is it? It's the t-score for approximately 95, what corresponds ultimately to a 95% confidence interval, okay? That can change depending on your sample and depending on a bunch of other factors where the actual number changes because the t distribution is an approximation of the normal distribution at high sample sizes. And I think I probably just lost everybody right there. But because the distribution isn't precisely normal, sometimes the 1.96 doesn't work. Okay, and so you have to actually look it up on the table and make sure that it actually does work, and then you can use whatever number the table gives you. But 1.96 is usually pretty good. If you were like, if you had to calculate a confidence interval on the fly and you didn't have a bunch of tables with you, I would use 1.96. All right, and this is a 95% confidence interval. All right, and in the paper, they're using 90% confidence intervals, and we'll talk about what that means and why. All right. So the confidence interval is basically the standard error multiplied by 1.96 to try to capture two standard deviations of that population curve. All right. So what they're saying is in your sample, the range of plausible values over many, many samples using your data to estimate it is going to be about this wide. 95% of the time, the confidence interval will capture the true population estimate. Okay. So this graph here is messy. It's 100 samples of tumor sizes. So, it's 8 tumors at a time. I think it's 8 tumors. Yeah. No, I can't remember. I can't remember the number of tumors they measured, but it's 100 estimates of tumor sizes when they take them out of people. And it's a simulation, so it's not a real tumor size thing, all right? But the true population mean of the tumors is 8. So this is sort of working backwards. If you randomly sample from this huge database of tumor sizes, right? what you'll find is that you have a mean, and then you have a 95% confidence interval around that mean. Okay. If you do 100 of these, there's some of them that don't actually capture the mean, right? Where are the other ones? This one over here, this one over here, and I think there's 3 more in here somewhere. So 7 of these don't capture the true mean. So that means when the way they did this simulation was they have a huge database of tumor sizes, and they just randomly sampled a small number of tumors 100 times. Okay, so if you do that, you get a graph that looks like this, and about actually 93% of the time in this particular experiment, the 95% confidence interval did not include the true average of the population, pretending that they had measured every single tumor in the entire world forever, right? So it's like it's a simulation of that. So a 95% confidence interval basically states that over the course of repeated experiments, the true population estimate is going to lie within the confidence interval that you calculated 95% of the time. Okay. And that's a roundabout way of describing it, but that is really probably the simplest way of looking at it, because it has to do with estimating population values. So in this paper, when they're talking about 90% confidence intervals, what they're saying is, if we did this experiment over and over and over again, the estimates that we have of injury risk would capture the true risk of injury for everybody across the world, right? 90% of the time. So there's a 10% kind of uncertainty that exists with the numbers that they're providing in this paper. So 95 is usually what we would say industry standard, right? Because it's I mean, 5% uncertainty is not horrible, right? You don't want to make it so high that you're going to miss things that are potentially important, but you don't want to make it so low that anything can pass through. So that's, and the 5% mark, that's why P is 0.05 in some ways, because, when Ronald Fisher wrote about why he set it at that, because that's who set it at 0.05, right? He said, well, this is generous enough that we're not going to miss things, but it's stringent enough that we're probably okay, right? And that is almost literally what he wrote. So,
Brian,
yes.
Could you just state the definition of a confidence interval one more time?
All right. So,
or just what it means. Just
yeah. So the confidence interval is interpreted within the context of multiple repeated studies. And a given calculated confidence interval basically states that if you were to repeat the study over and over and over again, that your calculated confidence interval would capture the true population estimate whatever percent of the time. So however you set that percent, in the case of 95%, your confidence interval has about a 5% chance of not capturing that true population estimate. All right. So in this paper, there's a problem, because the standard way to express a confidence interval, I'm just going to make a new page here. So if you write a paper, if you write a paper and you have a mean and you want to express the confidence interval in your paper, let's pretend your mean is 6'4". What you usually do is you put in square brackets your confidence interval, and you put the lower limit and the upper limit, and we'll pretend that the lower limit is 6'0". And some people will write 2, or they'll just put a dash to represent 2, and we'll say 6'8". Right? And then sometimes people will write 95% CI, 6'0" to 6'8". Right? You can't just put it in square brackets and not have any indication as to what you meant in the square brackets, because that could be anything, right? So, usually you'll write 95% CI somewhere in around that area. What you don't want to do is this. Okay? Which is what they've done in this paper, except they've used this crazy notation, right? So the reason why they've done this notation is because when you take the confidence interval of a relative risk, it involves a bunch of logarithmic calculations. And so you can theoretically, similar to how you get to here, right? By basically, let me get rid of this, or just for clarity, okay? So to get to here, what you had to do is you had your mean of 6'4", and you added, to get to the upper limit, 1.96 times the standard error of your population, right? And this number here was 4 inches. Okay. And then to get the lower limit, you did 6'4" minus 1.96 times the standard error. And this also should theoretically come out to 4 inches, right? So, if you wanted to be inappropriate but still express, you could theoretically write this plus minus 4 inches, 95% CI. But this is really unhelpful because it involves your reader having to do math. And it doesn't really, and when you get to a relative risk, now you're not dealing with a linear plus minus. Now you have to deal with a times divide. So now, like, when you see that on the paper, and like if you look at the paper, like, so here's just the first paragraph of the results section, right? So there's like, here, I want to use this to highlight things that I don't like. So there's relative risk number 1. There's relative risk number 2 at the confidence interval. There's 2 right there. To get this upper and lower limit, we have to like multiply and divide somehow in our heads as we read to figure out whether this is meaningful or not. Like, that's ridiculous. And then if you keep going through the paper, there is like literally nothing but this. Like, how many times are, like, your calculator is going to burn out by the time you get to like 3rd paragraph, right? Like, you're just constantly just trying to figure out what's the upper and what's the lower limit the whole time. So that's why it's so irksome, because you're like, well, this is completely confusing. Like, nobody can actually read this paper and get anything out of it on the 1st to 9th pass, right? So how many passes is it going to take for me to get through this thing? And it's been a month since we did it. And it took me 3 emails and a textbook to get to the answer that I'm going to give you today. Right. So, and that's with like a number of passes and a PhD. So, it's just like, it's so frustrating. Anyways, enough. All right. All right. So the 95% confidence interval for relative risk equation involves logarithmic calculations, right? So the 95% confidence interval, or the confidence interval for a relative risk, and we'll talk about what relative risk is after this, right, is actually defined by this formula right here, right? So the lower limit is here and the upper limit is here. And you get the lower limit by doing this crap, right? And this is 1.96 in quotations because, sorry, this is not, I keep doing this, 1.96 in quotations because that number can change, right? It's the t value for whatever percent confidence interval you're actually using, right? In this case, it's the t value that corresponds to 95%, but they would have used the one for 90% to get this, okay? So it wouldn't be 1.96. That's why it's in quotes, right? And so then to get the upper limit, you have to do the same thing where R is the relative risk, right? And you add, and you have to do another logarithmic calculation. So to actually get both the true relative risk and the confidence interval, we have to back calculate the entire paper. And there's like, I can't even count, like there's so many numbers in this paper. I don't know how you can read the paper and come away with it going, I need a spreadsheet. Like I literally need a spreadsheet to figure out this paper. And that's probably what I'll do in the next month, because that's the only way we're going to make sense of it. Like we actually have to do that work. So let's talk about, so first of all, I guess the first thing is, do you have questions about confidence intervals?
Can you tell me again the difference between standard dev and standard error?
Yeah. So standard deviation is a measure of variance, all right, in a sample.
In a sample, okay.
Yeah. So think about like when you run an experiment, you're doing a sample.
Yep.
Right? So you calculate a mean.
Population.
Yeah. And so then the standard error is theoretically the equivalent of a standard deviation for that entire sampling distribution.
You might call it the true variation.
The true variation given repeated experiments with the same sample size that you used for your original experiment.
Why does the sample size have to do with the error?
Because your standard error will get bigger or smaller depending on how many people you sampled originally in your experiment.
You sample 100%, your error is
0. So standard error is equal roughly to standard deviation divided by the square root of n for your sample, okay? So if you took, let's pretend for a moment, standard deviation equals 100 for some random mean. I have no idea what we're measuring, okay? So if n is equal to 4, because I can't do other square roots in my head right now, all right, then the standard error is going to equal 100 divided by 2, which is 50, right? If n is equal to 100, then the standard error is going to equal 100 divided by the square root of 100, which is 10, which is 10, right? So this number is unique to repeated experiments for which n is 4, right? And this number is unique to experiments in which n is 100, because your sampling distribution, this curve here, is generated by doing, because remember, this is frequency, right? So this is actually the number of estimates, right? And this is your, these are your estimated means. Right? So this value right here, sorry, this value right here is equal to the number of experiments with we'll say x with a mean of x, sorry. With means of x, right? So to generate this graph, you have to do the same experiment with the same sample size, because you're doing it over and over and over again. Does that make sense?
Yeah.
Okay. So that's why you, even though, like, I also like to think of it as the standard deviation of the population estimate, but you do have to remember that it is within the context of what's called the sampling distribution, right? That's this curve. This curve here is the sampling distribution.
Okay. Okay.
Okay. And so because of the central limit theorem, we know that sampling distributions tend to be normal, because you are eventually going, like, eventually, you know, like if you do it a billion times, you're always going to land here.
Yeah. Yeah.
Right? And the number of times you're going to get this is going to be very, very small, because that's not the truth.
Better.
Right? Okay. All right. So the next concept we have to talk about is relative risk, because that's the entire basis of this paper. All right. And so relative risk is basically comparing the risk of one thing to another thing. All right. Sorry. The relative risk is comparing the risk of one thing compared to not that one thing. Okay. So in the case of this particular paper, in the first paragraph, in the first results paragraph, so they said in the current week, a very high acute workload was associated with an increased risk of injury compared with all other acute workloads. Okay, and R stands for relative risk, and that ranged from, let's see, 1.9. Yeah, I don't even know how to interpret this anymore. Okay, anyways, we'll leave it there for now. I will figure the rest of this out later. Okay, so how do they calculate relative risk? Hopefully they did it this way. Two common terms in epidemiology are exposure and outcome. This has to do with the thing on our list about dependent and independent variables. Okay. So I like exposure and outcome for most clinical studies, or most like human studies, because it's not as, I feel like dependent and independent is a little bit confusing, and is not as intuitive, right? So when I say exposure, I'm talking about the thing that you're exposing someone to, and outcome is what you're measuring on the other side, right? So in this paper, the exposure should be training load or training volume. Whether it is or not, we will talk about. And the outcome is injury, right? So outcome is injury or not injury. There's only two. You're either injured or you're not injured, okay? And the exposure in that, for that first relative risk number that they published there, right, was very high acute workload versus not very high acute workload. So all other workloads. All right. So from that, you're going to get a grid of 4 numbers. Right? So every player is going to fit in one of these 4 grids on any given week, or however it is that they do the calculation. Okay. So if you were injured and you had a very high acute workload that week, then you're in column A, right? If you had a really high acute volume of training, but you didn't get injured that week, now you're in column B. So everybody falls into one of these 4, all right? So on and so on. So relative risk. So sorry, before I do that, so that's going to produce and then A plus B plus C plus D, right? So you get these totals, right? So A plus B is everybody that had a high acute workload. C plus D is everybody who didn't have a very high acute workload, right? A plus C is everybody who got injured, regardless of workload. And B plus D is everybody who didn't get injured, regardless of workload. Make sense? So relative risk is, let me just make sure I get this right. Yeah. So it's A divided by A plus B divided by C divided by C plus D. So in this particular case, this term here, right, is all high injured divided by all high. So what percentage or what fraction, sorry, not percentage, what fraction of everybody who was exposed to high volume got injured? C is not high, injured, divided by C plus D, which is not high. So you're comparing injury rates between high volume versus not high volume, right? So when you think about relative risk in terms of how you remember how to calculate it, because this grid can shift around depending on how you put these little guys. right? I always try to keep exposure on the side and outcome at the top so that I don't, because if you do it the other way around, now you can't do it. You have to like think it through again. But it's basically everybody who you were interested in who got like, who basically ended up with the thing that you don't want them to have, right? Divided by the people that you're not interested in who also got the thing that you don't want them to have, right? So that's relative risk. You'll run into, eventually, you'll run into a thing called an odds ratio. And these two concepts are linked to one another. The odds ratio has more to do with when you actually have control over your control and your not control group numbers. So where you'll find that you have to use an odds ratio is when you talk about a case control study. And we're not going to do that today because this study doesn't use odds ratios and isn't a case control. So it's really hard to illustrate it in a concrete way without being completely abstract. But know that those two concepts are different. So if you see a relative risk and the design is a case control, you know right away that whole thing is going to be bullshit. Okay? And vice versa. So if it's a case control study and they're talking about relative risk, you have to read it really carefully to make sure that that isn't complete crap. Yes.
So then what studies are you going to see predominantly using relative risk, or what study designs?
Yeah, so relative risk is basically, so the difference between, okay, so we are going to talk about this a little bit then. Okay. So all right, so you have these two concepts. You have exposure and you have outcome, okay? And some people like to call this, some people like to call exposure the independent variable, and the outcome is the dependent variable. Dependent. All right. Dependent is what you're measuring. So its value is dependent on the stuff that has already happened. Right? So from in a temporal sense, exposure almost always comes before outcome. Like you can't have an outcome before you've been exposed. Right? When you're designing a study, you can pick, these are more, yeah. So when you're designing a study, you can design a study to look at how exposures are different and how they produce different outcomes. So smoking is a good example, right? So you can look at smokers versus non-smokers, and then you follow them forward in time and you see who gets lung cancer. Okay, that's what we call a prospective study. All right, and something like that is where you would use a relative risk. Okay, because you can't, because you're not controlling the number of smokers versus non-smokers. Sorry, you're not controlling the number, sorry, that's the wrong answer. You're not controlling the number of cancer versus not cancer patients. You have no control over that, right? You have no idea. You're like, does smoking cause cancer? So I'm gonna look at a bunch of people who smoke and a bunch of people who don't smoke, and then I'm going to, 50 years down the road, I'm going to see if any of them have cancer. Okay. That is a very impractical experiment if you're trying to figure that out, because now you have to wait 50 years. Okay. So the other way you can do the experiment is to go the other direction, where you select patients based on their outcome and you look backwards in time to see what exposures were different. All right. And that's called a case control study. So you actually pick like 50 people who don't have lung cancer, and you pick 50 people who do have lung cancer, and then you look at whether they were smokers like 10 years ago, let's pretend, right? So you have no control over whether they were smokers or not, but you have full control over whether they had cancer or not, whether they come into your study or not, right?
So is that the same as a retrospective cohort then?
So yes, technically it is the same as a retrospective cohort. I subscribe to the prospective and retrospective as what you're selecting your sample on. Not everybody agrees with that terminology, even though I think that is the most correct way to do it. So if somebody says there's a prospective cohort, that's because they basically measured them at time 0 and are following them forward to look at their outcome, right? Versus retrospective, which is when you're actually picking them based on their outcome and then looking backwards to see what their exposures were. However, in the literature, you're going to find vastly different designs using the words prospective and retrospective. That's not going to match that definition, which is why it's tricky to just blanket go, yeah, you can go ahead and do that, right? And also why you should never take someone's like statement of design on their paper as granted, because most of the time it's not most of the time, but a lot of the time it's not, right? Somebody says, oh, we did a retrospective study on this, and you read it and you're like, no, this is actually a prospective study because you're looking at exposure and you're measuring outcome, right? So the odds ratio is used for when you're selecting on outcome and you're measuring exposure. Because if you think about it, you have already predetermined the number of each outcome that exists in your study, right? So if we do our ABCD thing, right? And this is, that's really messy. Exposure plus, exposure minus, outcome plus, and outcome minus, right? So A over A plus B and divide by C over C plus D is our relative risk, right? But I actually control, I control all of these. I actually control all of these numbers when I design. I control this column here and this column here when I design a case control or a retrospective study.
Okay. So,
right?
Okay.
So
because you've pre-selected the outcome.
Right. So let's say, let's pretend I was doing this smoking lung cancer study, right? I could say, okay, so I'm going to have 100 people with cancer, and I'm going to look at 100 people with no cancer. And then right? And then I'm going to say, okay, well, 90 of the cancers were smokers, and 10 of the not cancers were smokers, right? That's what I ended up measuring, right? The problem here now is, so what is 90? So 90 is cancers who were smokers. So that's going to be here, right? And 10% of not cancer were smokers, right? I've biased this information automatically because if I had taken 1,000 cancers, not cancers, and let's say the percentage is the same, right? Then this is going to be 100 not cancer smokers. This is now 100. So when I do this, so just the term, the A over A plus B term is going to be 90 divided by 90 plus 10, or it's going to be 90 divided by 90 plus 100. Depending on how many people I decided to cheat with, because you could cheat a relative risk if you get to pick the outcome, right? So if I want to show that smoking doesn't cause cancer, then I pick 100 cancer patients and I pick 1,000 people who don't have cancer, because now it totally looks like they don't get cancer. Right? So that's why you can't use a relative risk when you control the numbers like that, because you don't have to sample equally. You don't have to say 100 and 100. You can do whatever you want.
So to kind of summarize the difference between these two things, if I can, with relative risk, you're almost like what you are trying to control or apply or pre-select. That's not even the right term, but you are dealing with, I'm applying this exposure and I'm seeing what happens.
Right.
And that's why it's prospective, because you're looking at the endpoint.
Right.
With the odds ratio, you are pre-selecting the outcome. So you're saying, look, this is what happened. I'm going to see if the thing that I would have applied was true for that given population.
Correct.
Okay.
Yeah. And when we eventually get to a study where an odds ratio comes into play, then we can talk about what that means, because odds are very non-intuitive. In fact, I'm not sure I totally get it in my own head, but because odds, the reason why you can use an odds ratio is because odds include the probability of something not happening as well as the probability of it actually happening. So if you flip a coin, 50-50 heads tails probability, the odds of flipping a head is a 1-to-1, right? You've heard that before, 1-to-1 ratio of odds, right? So it's the odds of something is the probability of it happening divided by the probability of it not happening. So when you flip a coin, it's 0.5, sorry, not 50. Probability is 0.5 divided by 0.5, which is 1, which is why it's a 1-to-1 odds. Which is why in Vegas, you have odds, because you are betting on something happening versus not happening. You can't have them both happen at the same time. Okay, I think we've run out of time. See, I told you probably only get through 1 or 2. So, all right.
That was incredibly helpful, Brian.
So, sorry, this thing doesn't let me jump. Sorry for the dizziness there. All right, so what did we do today? We did this. And we did this. I think we did this. All right. So next time, I think I will try to tackle, I think this one here is going to be better to tackle. And then hopefully we'll get to this one here as well. And this one I'm going to leave till last because it's, the idea of validity is going to take up a whole, I think it's going to take up a whole hour. So, all right. And then we can actually finally talk about the paper, right?
Maybe.
Yeah, right.
We're really gonna know that paper though.
But you, well, A, you'll really know the paper, but B, like you'll actually you'll read it with different eyes. You'll probably read it with different eyes even if you go through it now again.
Yeah.
And you're sort of like, what, right? And I think I will probably do the spreadsheet for next time.
Oh yeah.
Just to actually say, like, because those numbers are like so confused. Like you have to take out a separate piece of paper to figure out what this paper actually means, right? Like, can I use this information or can I not use this information? And that is on the basis that this information is actually already being used, right?
Yeah.
Which it is.
So
I mean, we were talking about that. We just, that part we just had to skim through.
Yeah.
Yeah.
But it's kind of like, okay, well, so if you put this into use, then how did you figure out whether that was okay or not?
Yeah.
And for us to sit here and read it, it's like a month later and we're still no further ahead in really being able to figure out whether or not this should be used. Right?
Yeah.
Now, we're not spending like 24/7 on the paper, obviously. Well, you guys aren't, but it's occupied about a week of my time, but
I just shoot first and ask questions later.
Right? But it does beg the question of, okay, so if you implemented this, on what basis did you implement it? Like, where did you go with this? If this was where you decided to hang your hat on whether you're going to implement or not. Obviously it's not, because it's a whole body of literature, right? But if this is a critical component of that body, then what just happened, right? Mm-hmm. And that's part of the whole evidence-based paradigm, which is if you can't analyze it, if you can't understand it, then you can't use it, or you can't knowingly use it. And then you have no idea what's going to happen afterwards, right? And that's why this portion is so important in being able to say, okay, every single word you don't understand, we have to go through, right? So when you go through the paper again, like you probably just need to skim it again this month, I think. But if you're seeing new words that are popping up, they're like, okay, I get that. And by sort of process of subtraction, you're like, oh yeah, this word is popping out at me now because I get these other ones and I didn't notice this other one before because I was so distracted by the fact that I didn't get like 3/4 of what I was reading already, right? So it's useful to go through again and go, okay, so now that I've gotten these 4 concepts out of the way, that's actually closer to 5 or 6 concepts that we've really done, right? What's left? What's left in this paper that is still puzzling, or these words don't make any sense, right? And we will come back to the confidence interval thing because I think it is important that we do the back calculations and really see, because I just did the back calculation for just one of them and it's not good, right?
Right.
Like because the interval is so wide that the range of plausible values is crazy, right? Like the precision is very off, right? Anyways.
So then, like when you're appraising an article of some sort and for your practice, how much time would you say you put into a given? Like, I mean, is this now? Obviously, it's probably a little bit different because you're also having to explain things to us. But
right,
is this your norm?
Oh yeah.
Wow.
I mean, but this is the norm when you have dedicated a lot of time in developing the skill to read, like the skill to critically read.
Yeah.
Right. So over time, and the reason, you know, I mean, critical mass is a name that I picked on purpose, is because once you develop that critical mass of concept in your head, you'll start to read these papers and you'll be like, oh, okay, I don't need, nobody needs to explain this to me anymore. Like, I know what these words mean, and it goes much faster because you just get more. Right now, it's like, if I get a paper, I mean, I have 2 peer reviews sitting on my desk right now, right? And it's like, oh yeah, so I'll go through them. It takes me about 4 hours to like go from start to finish and write it. Like, for it to be completely gone off my desk, it takes about 4 hours, right? And most of the time, I don't need to look anything up. I don't need to do anything. I'm just basically scribbling on the manuscript itself, and then I take the scribbles and I transfer it into a Word document, and then it goes, right? Because I don't have to think about this or that. Sometimes I'll have to look into their references, and that takes time, right? And we'll do that a little bit in this paper too.